Okay, welcome to section 2.3. This is day 1, continuity. I'd like you to go ahead and pause the video and copy the diagram and answer these questions. If you don't know how, you can watch a couple of these done for you and then pause it. Okay, well hopefully you gave that a try and you've got that copied down onto your notes. I'm going to go over these now. Again, if you haven't done these yet, please pause it and try them. Okay, so remember what this means. This means to find the y value when x is -3. So for this graph, that's an x-intercept. Y value is 0. Okay, and for -2, I've already labeled the y value as 1.5. Okay, for -1, you're going to have to choose between these two locations on the graph. And actually there's only one answer. The answer is at 2, not up at 3. This indicates that the point is not present. The function is actually evaluated at wherever a vertical line drawn would intersect the curve. So if you were to sketch a vertical line in here, it would definitely coincide with this point and pass through there without touching the graph at all. So the graph does not exist here, it exists here. Okay, so it is 2, not 3. F of 0 is this point 0, 1, so the function value is 1. F of 1 is up at 2 again. You can see that's the same as for -1. F of 2 really doesn't exist. There is no point above or below x equals 2, 1. That's our empty space there. It's called a hole. So we're going to go ahead and put undefined for that one. For this one over here, this is an x-intercept again, so we'll put 3. We'll write x-intercept. And we forgot to write y-intercept here. Let's go and put that in. Okay, f of 4. You can kind of see my answers here. They're off by 1 because I had mislabeled these originally. But okay, f of 4. F of 4 is 1, 2, 3, 4. You're going to have to choose between these. We'll go with the darkened point. It's -2. F of 5 is at +1. F of 6 is undefined again, but for a different reason from before. F of 7 is another x-intercept. And f of 8 is at -2. Okay, so your f of 6 is undefined because of this vertical asymptote. Again, there's no way that this vertical asymptote can touch any portion of the graph, meaning that that graph is not defined at x equals 6. Remember, a graph cannot cross a vertical asymptote for a single function like that. Okay, so there it is. Okay, we're going to be studying discontinuity in an effort to understand continuity. Let me just give you a basic feel what continuity means. Continuity has to do with the smoothness of the curve. I should say actually the connectedness of the curve. So you can see here that portions of this curve can be drawn without lifting your pencil. You can draw this entire left-hand portion without lifting your pencil. It will take you a long time, take you off to eternity to do. But once you get to here, you find that you can't connect to this part without lifting your pencil off the paper. So there's a point of discontinuity at -1. This part of the curve is smooth until you get to +2. And at +2 we have another break in the graph. And then again it happens down here at +4. It happens at 6. There's a gap there. And then this part can be drawn smoothly. That's a darkened point there. Okay, so there are points on here where the graph either disconnects, basically disconnects, and needs to be, it would need to be filled in if we were to have connectedness, or the word is continuity there. Okay? Alright, so that's the intuitive idea. A couple of these are removable discontinuities. For example, this one here. All I would need to do for this function is assign a value for this point, x equals 2. If I could assign f of 2 to be 1, then that would fill in this hole and that would be removable. And on this one I would just need to reassign f of 4 to be -1 instead of -2, and that would fill the hole. So these two kinds of discontinuities are called removable. The others are not, and they have different names. And we'll go over all that right now. Okay, let's draw a new graph. Alright. Okay, for our second diagram, we're going to draw something a little bit simpler. We'll keep everything either on an axis or in quadrant 1 for this one. We're only going to need to go up to 1 here, and we'll go out to 4. Good enough. Okay. Okay, so we need a point here. This is a closed point, and an open point here. Alright, and then pick it up here with a closed point, and an open point. We'll need a point up here at 2. Closed one. And up a space. Sorry about that. Alright, so this is 1, 2, 3, 4. This is 1 and 2. Turn off that light there. Okay, so you can see the points, I hope, there. I hope it's not too dark here. Okay, everybody have that copied down? Okay, so we're going to do a discussion on points of discontinuity to help you understand a little bit better. And try to take notes in pencil, because I decided I'm going to go ahead and make this an open point here. Okay, so points of discontinuity are any points either in or not in connection with the rest of the graph. So let's see here. This point is considered continuous even though there's nothing on the left side of it. So we were talking about how you can connect smoothly without lifting your pencil to draw the graph. Well, a starting point on a graph is included as a continuous part of the graph. So the first discontinuity we actually run into is right here at 1, where the graph skips upward to this point, and the graph is defined to be at y equals 1 between -1 to +1, including the 1 and not including the 2. Sorry, from 1 to 2 I meant. Including 1, it's at height 1. When we get to x equals 2, we're not including 2 as a piece of this piecewise function. Rather, the point is defined to be up here. Alright. You could actually write off the function for this. It wouldn't be very difficult to do. They're all straight lines. Alright, so let's go ahead and take a look. This first one is at x equals 1. And this second one is at x equals 2. And the third one is at x equals 4, actually. And they're all discontinuous for slightly different reasons. Alright, here's how you show a test for continuity. And I do need to emphasize that this kind of thing is very important. And not enough to just recognize where a graph is smooth. I gotta stop using that word. It's smooth. We'll refer to something a little bit later, something a little bit different. But rather connected. We don't want to just know that it's a connected point. So what we want to do is show the following test. We'll start with x equals 1. We want to take the limit as f of x as x approaches 1 from the left. So that's going to give us limit x positive 1 from the left of f of x. That's just the y value we're approaching as we come in from the left. So that's approaching the x-axis, so the limit is 0. Then we do that from the right side. Okay, this is different. Since we're coming from the right side, we're on this segment, and the point of approach is actually y equals 1. We're not approaching the x-axis, so that's 1. These two combined we would write it as limit as x goes to 1 in general of f of x, what? Does not exist. Remember, these have to agree for the limit to exist at a given point. Okay, that refers back to section 2.1. Okay, now we check the function value at the point f of 1. All right, well, f of 1, we would choose between these 2 points, and we would go with this one up here, which is 1. Now, in order for there to be continuity, we need this first answer that we got and this second answer to agree. And then the third answer would be that number, and then that would have to agree with this number. So in other words, these would have all had to come out to be 0, or all had to come out to be 1 in order for this to be truly continuous at x equals 1. All right, so in other words, the graph must approach from both sides and be defined to have the same value in all cases. You need the left limit, the right limit, and the function value to agree in all cases. All right, let's try it from 2 now. You can see on this one, things are a little bit better. We're approaching 2 from the left, and it's at height 1. The same is true if we're approaching from the right. We could even combine those to declare the limit in general at x equals 2 is 1. But the problem is f of 2 is actually 2 because the point up here is shaded. So again, we have a point of discontinuity for a slightly different reason. We had agreement here, but at the very last minute decided no, can't do. Okay, so that's the point of discontinuity. Okay, x equals 4 is discontinuous for the following reason. This is a different kind of discontinuity. I shouldn't say different kind of discontinuity, but it's an endpoint, so it's tested a little differently. You won't be able to test the left limit and the right limit, but rather only the left limit, because there is no graph over on the right at this point. So for this, the requirement is a little bit simpler. We just have to make sure that the left limit agrees with the function value. So the left limit is the graph descends down onto 1, but when it comes time to find f of 4, we don't have that. There is no f of 4. It's undefined. Function is not defined at x equals 4. Okay, so you can see that for an endpoint, we're going to just have to test one side, and it should agree with f of that value. Okay, we'll come back in a minute and we'll test a couple of these points for continuity, but I think learning continuity is a matter really of finding points of discontinuity in this case. Okay? All right, so let's see if we can write down a formal definition of continuity. So what exactly is the formal definition of continuity? I like to do exercises where you have to kind of figure out on your own what something means and then try to form a definition. There will be days when we just give the rule of the day and attack problems with it. But I think discovery is the best way, and summarizing is the best way in a lot of cases. Okay, so obviously it's not always going to be a 1 here, right? It could be any value. So we would call that C, like we've done in the past. Okay, so we would want the limit as x approaches C from the left and the right and in general to all agree, right? I should say the left and the right to agree. Therefore, that would make the limit at the point defined. All right? We would then, that's for f of x, and we would like that to equal the same thing as if we had just plugged in C. So we can fill this in. A function f of x is continuous at an interior point C of its domain if the following is true. Okay, so we kind of stumbled across it as I explained to you what discontinuity is. It would seem then that what we were really looking for in our search for continuity was that this limit would agree with the function value at the point. So it's all kind of simple, really. 2 tests on the left and right, 1 test to see what the point is. Now that's for a point on the interior. Okay. So sort of the part B for this would be a function f of x is continuous at its left endpoint A. Now not all functions have a left endpoint, or any endpoints for that matter, but if it does, it is going to be continuous at its left endpoint A if the following is true. You could probably figure this out on your own, but now for a left endpoint you would be coming from the right. The limit as x approaches A from the right for that function agrees with the function at the right, or at the endpoint. Okay? So it's the same statement as above, it's just one-sided. And lastly, a function f of x is continuous at its right endpoint B. Bring this up a bit. If the following is true. The limit as x approaches B from the left of f of x, you don't need the double brackets there, is equal to f of B. Okay? Okay, let's just go back to the graph here real quick and test for a couple of the points that we know are continuous to show that they're continuous. This is, by the way, this really needs to be memorized word for word. Not all things in calculus have to be memorized for the AP test, but the wording here is very important. And there's this phrase of its domain. This is going to be very, very important tomorrow. Let's go ahead and take a look at, let's look at the point x equals 3 on here. Okay, so a test to show that f of x above is continuous at x equals 3. Alright? If you want to pause it real quick, you can give it a shot, showing your work. As obvious as it is that the graph is connected there, we still need to show our work to show the test. Okay, so let's go ahead and do a left limit. I'll do the work, and hopefully you paused it and tried it yourself. Alright, so we'll do a left limit for x equals 3. Okay, let's go back to the graph and take a look. What's the limit on the left here? As you come in towards x equals 3, you find yourself up at y equals 3. Okay, so it's 3. Or I should say 2, not 3. So 2. the limit as x approaches 3 from the right is also 2. So we can summarize this to say that the limit as x approaches 3 in general is 2. Not to mention that f of 3 is 2. Okay, so this right here confirms continuity. Okay? Alright. A test to show that our left endpoint is that our graph is continuous at its left endpoint. A test to show that f of x above is continuous at x equals 0, which is in the domain. Okay, so we'll just do a right test for this point. We don't have a left side here, so from the right, I got 1. You can take a look up above and confirm that. And f of 0 is 1. So this test is simpler for an endpoint. There it is. I do need to do one thing here, a slight formality change on my graph. So after you copy this down, I need to move the paper here. Okay, so let's go back here and look at this. I'll show you what I meant. I was talking to you about the continuity at an endpoint, and how at x equals 4 we were saying that the left limit did not agree with the function value at that point. So what I'd like to do actually here, for the sake of our notes, is just to have this have a point here, and then on this part of the example, just go ahead and erase undefined and put 2 there. Okay, so if you could just make those corrections, I think it helps us a bit, and it just avoids the question of, well, was 4 ever in the domain? Should we even have considered it? Okay, one of the graphs that's fairly important is the integer function. We saw it actually in the first lesson of the book. Okay, this is the graph, remember, where there's a closed endpoint. It goes one space over to 1, and then there's an open point, and then another segment at the same length here, and so on. So you might remember seeing this graph from the first lesson. This just goes on this way, and then basically it's a step function. So just if you could take a moment and draw this one, we'll take a look at this graph from the same perspective. We just want to find points of continuity and points of discontinuity. Okay, so this is called the integer function, the greatest integer function. Sometimes drawn like this. But we'll just write int. In your calculator, your TI calculator or Casio or whatever you have uses int, and you can find it under the catalog. You can even graph this in your catalog. Your calculator, go to y1 equals, and then choose catalog, choose integer function x. y1 equals this, int x. Okay, so basically it's easy to tell where the points of discontinuity are. Basically at every integer. And to show that, we would just simply state that the limit as x approaches, and we'll just do 2 for the sake of argument, and then we'll summarize. Because we'll go ahead and use n. We don't need to use numbers all the time. As we approach any integer from the left versus approaching it from the right, we're always off by 1. Okay? So, and we won't write f of x here. We're going to write intx. Sometimes you want to go ahead and write the actual function there. Okay, sorry for jumping back and forth, but if you look closely at this, anytime you come from the right, let's say you're coming towards 2 from the right, the y value is 2. But if you come towards 2 from the left, the value is only 1. See? So that's if we're doing 2. If we're doing 3, then these numbers would be 2 and 3, and so forth. I'm sorry, if they were doing 3, then this would be 2 and 3. So basically, this is always going to be whatever your value is here, and this will always be 1 less than it, which just means that the step on the left is 1 space lower than the others. So that right there, that's proof. And when you actually find int of n, when you actually check the function value, you get n every time, but these 3 don't all agree. So this is equivalent to saying limit from the left of f of x, limit on the right-hand limit of f of x, and f of x don't all agree. It's the same thing we did up above, we just used intx, and we're using integers only. Okay? So the points of discontinuity are these, every integer. Therefore the points of continuity would be everything else in the domain. And actually, what is the domain of this function? Technically, this function has domain all real numbers, because for every x available to us, there's always a y value. For every open hole even, there's a point above it to fill it, so to speak. So there you go. Graph is continuous everywhere except at integers. Alright, so the next thing we're going to talk about is we're just going to try and summarize all of these different kinds of discontinuity points, because I mentioned something earlier about removable discontinuities. Well, the book does a nice job laying out all the different kinds of discontinuities, and they use a straight line for it. I thought maybe I could use a curve. That way you have my example and you have the book's example of it. But continuity is just basically when the limit on the left and right agree, and the function value agrees. So basically it's a completely smooth curve at that point. Alright, so the example we could do is if you had a parabola here, they use a line, but this is continuous at x equals 0. This one drawing the same function, this time with an open circle at x equals 0. This is discontinuous. And this point would be called a hole. The third one we could have a hole here and a point above it, which is not located within that hole. But these two would be considered removable. So if you think you remember what I had said about that, then you should probably pause the videos and see if you can say it out loud. Okay, did you try it? See if you can recall what I had said about these. Okay, what I'd said was that the reason these are considered removable is because all that would need to happen is that someone would need to tell you what the y value of this function, what y value we should put in when x is 0. So the person could say, okay, let's include f of x is 0 when x is 0, and then that would fill that hole, and the graph would now be continuous at x equals 0. Alright, and then in this diagram, we would need to reassign f of 0 to be 0 rather than 1, bringing this point to the origin. So it's removable. Okay, and then the book goes on to show some other kinds of discontinuities that are not removable. Okay, so one of these is where the graph comes down. Maybe this is, I don't know if this is a parabola or what, but it looks like a y equals x squared graph on the left. And then maybe we have, let's do a close point this time here. And then maybe up here at 1, the graph is that of a line starting with x equals 0 to infinity. This is now a line. Okay, this is a classic piecewise function. You recognize it from pre-calculus. This one is also obviously discontinuous or not continuous at x equals 0. And this has a name here, these problems. This kind of discontinuity is called a jump discontinuity. That's a great name for it. Sorry about that. Okay, this one is not removable. You would actually have to redefine the entire right side of the function, shifting it all down to space to get it to join up with this portion of the graph. Or you'd have to take this half parabola portion and move it up to fill the hole. So this is not removable. Okay, another kind of discontinuity that is not removable is the vertical asymptote. Okay, so you've seen this before. You might have a graph that goes like this on this side, and then maybe comes down on this side. So again, f of x is not continuous at x equals 0. This is a vertical asymptote. And this also is not removable. You would have to remove the asymptote and see if the graph connects then. So this is not removable. And then the last one that they give, they actually don't explain it a whole lot. It's called an oscillating discontinuity. Oh, by the way, this one is called an infinite discontinuity, if you must know. This last one is. Okay. The oscillating one's a little bit harder to follow along with. So you probably remember sine of x. Well, what would sine of 1 over x look like? Well, sine of 1 over x would have serious issues here. It does oscillate between -1 and +1. It is a sine function, sort of. It would not include x equals 0 just by virtue of the fact that we can't have sine of undefined. So we know that f of x is not continuous at x equals 0. That goes without saying. But what exactly is the feature at 0? Is there an asymptote there? Or is it that the graph jumps and doesn't agree on either side? What's going on? Well, the problem is the function never actually quite reaches 0, but it doesn't have this behavior where this part goes up to infinity and this part goes down to -infinity. Remember, it can't go above 1 and it can't go below -1. So what exactly happens? Well, if you plug in larger and larger values of x, which means you're going out to the side, this graph just continues to oscillate between -1 and 1. So for large negative numbers, let's say, let's say that x is -1 million. This is practically sine of 0, and actually this diminishes down over here. Same thing out on the right. Okay, when you get closer in and actually throughout, you're dealing with 1 divided by, say, 0.1. Now that's actually a larger number. That's 10, right? Sine of 10 degrees or sine of 10 radians. We use radians for this stuff. Or think about it if it was 0.01. This would be sine of 1 over 0.01. That's 100, sine of 100, right? And we know that you can make these interiors big or small, but the answers come out between -1 and 1. So what happens in here? Well, basically, the function starts to lose period. Same thing from this side. I mean, it maintains that idea of wiggling back and forth, but it doesn't actually meet in the middle. So this is considered oscillating discontinuity. It's really impossible to imagine what happens in the middle. But it's not the same idea as this one at all. And it's not the same as this one. It's its own thing. So we call this an oscillating discontinuity. You could zoom in forever on this and find that it's still not hitting the actual y-axis, and it's also not behaving in any agreeable way on either side. Oscillating discontinuity. Alright? So those are the various kinds of discontinuities. So what would be very, very important right now is to go back to those two removables and talk about how to make an extended function. Okay, the last topic here would be to talk about those removable discontinuities from earlier and talk about a way to define what's called an extended function so as to fill in those holes or to reassign the points to fill the holes. Okay, so your example for this that I'm going to use is the following one. Okay, this is not the one the book does. You can look at that one if you need another example of what to do. Okay, this one is to give formula for the extended function extended, sometimes these are called continuous extensions, extended function that is continuous at the indicated point. The underline is. Sorry about that, zoom out of it. Okay, here's the example I chose. F of x is equal to x cubed plus 8 over x plus 2. Okay, so remember the first thing you really want to do is to double check the domain, right? Okay, so let's check. We do have a discontinuity at x equals -2. That comes from the fact that the denominator shouldn't be equal to 0, so we have a discontinuity here. What kind of discontinuity is it? Well, the most important thing to do is to check the numerator here and to factor it out to see if that x plus 2 is removable, or if it can be canceled. Okay, so I don't know if you remember how to factor a sum of cubes, but this one factors into x plus 2 and x squared minus 2x plus 4. Okay, this uses the SOAP rule that you learned in Algebra 2 Honors. Okay, so our function now looks like this. F of x equals x plus 2 times x squared minus 4x plus 4 all over x plus 2. And we can see how this, although negative 2 is not in the domain, it can be removed. It is shaped as a parabola except at negative 2, where we find a hole. Okay, so this was the removable discontinuity. So x equals negative 2 is a removable discontinuity because x plus 2 canceled. So first it has to be a discontinuity, and then it canceled out. This means the graph has a hole. At x equals negative 2. Aside from that, it should be shaped as, sorry, this is a 2. I just copied it wrong from up above. It should be shaped as x squared minus 2x plus 4. So let's just draw a quick sketch of it. Okay, so our function is f of x equals, you don't have to rewrite it, I need to, because I grabbed a new sheet of paper here. It's a parabola. Let's go ahead and graph x squared minus 2x plus 4. So vertex would be at negative b over 2a. Actually, let's complete the square. We can complete the square here. It's good practice for us. Alright, so you'll be adding in a 1 to complete the square here. We'll put it in standard form. Alright, so insert that, and we get y equals x minus 1 squared, we have to take away 1 here, plus 3. So vertex is at 1, 3, opens up, because this is positive, and it's of course a quadratic. So we're dealing with this graph here. 1 and then up 2, 3. It actually passes through 4. You can see the y-intercept here when it's back. When you're back up here in this form, y equals ax squared plus bx plus c. That c is your y-intercept. So by symmetry, you have a point there. Okay. If you plug in, actually, if you plug in negative 1 here, you get 7. So here's your curve. Okay, if you were to follow this parabola over on the right and plug in, let's say, 3, you would find that you're up at 12. Because this is going to give you, I'm sorry, if you plug in, sorry, this one's at 2, 4, this one's at 3, 7. If you plug in 4, you're up at 12, because it gives you 9 plus 3. Well, that would happen on the left, except that we have a hole there. So what we just discovered is where that hole is, exactly. That hole is at negative 2, 12. In the same way that 4 spaces out to the right of our vertex here leads us up to 12. Okay, so that's where the hole is. And that could easily have been found by taking negative 2, which is our discontinuity, and plugging it into this portion. Did you hear that? Plug in negative 2, which is our discontinuity, into this portion. Okay, so to find the location of the hole, plug C into the reduced version of f of x, and that is no longer f of x. It's a reduced version. So, but you can think of it this way. All right, so we'll take our -2, plug that thing into the reduced version here. This gives us that 12, but we also saw it from the graph. Okay, so f of x has that hole, and there's nothing we can do about it, but we can create a new function that fills the hole. Now it would have to be basically f of x, and then it would have to include the point -2, 12. So here's how we would write that. We would go ahead and say that g of x is f of x, and list the domain there. And then we would also want for x, or this is -2, for x equals -2, we would want to go ahead and let the function g of x be 12. So we create our own function. This is the extended function. And this function does include everything that that parabola would need, and the graph would then now be continuous at x equals -2, the way it is with all the other points. So this is now continuous, even though it's not necessarily f of x. We would call this thing the continuous extension. Extended the formula a little bit and filled in the hole. Okay, so I typically go pretty slowly through this. It's not so much that I think you need me to, but rather when you are hearing it and writing it and reading it as you write it, and I go slow, you have a chance to glance back and forth. And I realize this takes some time for you, but it takes time for me too. So don't forget to go back and look over the things that you need to memorize, and just maybe write a couple sentences about what you learned today. Try to use the proper terminology as usual. And we'll continue section 2.3 next time.